Hi everyone. In the case of uh, continuous type random variables, as we discussed earlier, we define the probability uh, density function in terms of or from the definition of probability what we call distribution function, or the derivative of distribution function is the probability density function of a continuous type random variable. And uh, if we have a continuous random variable, then usually we start with the concept of omega, the sample space, and the event space, capital A. For a discrete type random variable, uh, this we can have the event space as the power set of sample space. That is, if you consider the set of all subset of the sample space, then that will function as the event space of a probability which is of discrete type. But in the case of continuous random variable, uh, usually we are going to okay, the set of all subsets uh, will function as an event space in most of the cases, but um, somewhat something more proper or appropriate uh, in terms of some properties is um, the Borel algebra or Borel sigma algebra. Borel sigma algebra defined on the sample space omega. Borel sigma algebra is a collection of subsets of omega which contains some which have some desirable properties. It does not contain all the subsets of omega, but the is a collection of subsets uh, which have some desirable properties is known as a Borel sigma algebra. And a Borel sigma algebra defined on the sample space is usually considered as the event space in the case of a continuous random variable. Then, if we look at a random variable x and a probability density function f of x, whether it is continuous or not, then this f of x has two important properties. One is f of x is always positive, and the second one, if we sum up for all possible values of x, then this will add up to the value 1. If it is a continuous one, then we integrate from minus infinity to plus infinity, f of x equal to 1. These are the two important properties which we can associate with a probability density function of any random variable which may be a continuous type random variable or a discrete type random variable. Then again, in a similar way, if you have a cumulative density function or df distribution function, then for any df, f of minus infinity is equal to 0, f of plus infinity is equal to 1, and the function f of capital F of x uh, is a left continuous function. These are some properties of capital F of x. And now we are going to have a discussion on some important results or theorems uh, on probability, namely the rule of sums or sum rule, then product rule, and another important theorem which is known as Bayes' theorem. So in this case, uh, these are comparatively some results which can be obtained from our uh, natural sense, and this is for, say, if you have two random variables, let x be a random variable or x and y be two random variables, x comma y be two random variables, and p of xy be the joint probability density function, which is technically defined as p of xy is equal to probability that capital X is equal to small x and capital Y is equal to small y. The joint probability density function of two random variables, capital X and capital Y. Let it be either continuous or discrete. For the time being, um, is not so much important. Then, so when p of xy is the joint probability density function of x and y, and uh, x and y are two random variables, then we denote uh, small p of x and p of y. They represent the marginal distribution of x and y. So in some cases, some textbooks use the notation fx of x and fy of y to represent the marginal distribution of x and y respectively. So that's another representation, which is more common. But I think this p of x and p of y is very straightforward representation of marginal distributions. If the situation or if it is directly implied, uh, this particular notation is self-explanatory in our particular situation. The second one is a more complex notation to represent the marginal distribution of x and y. Anyway, the marginal distribution of x is defined as to find the marginal distribution of x from the probability density function p of xy. What we have to do is we sum up with respect to y. Summation for all values of x, y, p of xy gives the marginal distribution of x provided the density function, the random variable y is of discrete type. And if y is a continuous random variable, then we integrate p of xy, the probability density function, with respect to y. And in a similar way, the marginal distribution of y can be obtained by summing up with respect to x, p of xy, and is equal to the integral p of xy dx. So this is the marginal distribution. And if x and y are two random variables with the joint probability density function p of xy, then we can define another probability density function p of y given x is read as p of y given x, and p of the probability that x given y, probability of y given x and probability of x given y, both are defined as p of or the values of p of y given x is given by p of xy divided by uh, p of x, and p of x given y is given by p of xy divided by p of y. So remember, the numerator is the probability density function, joint probability density function, and in the denominator we have the marginal distribution. So that is how we find out the probability distribution function of y given x and x given y. We will illustrate the concepts using a simple example in our discrete case. Okay, so let us consider an experiment of a random experiment in which we have two random variables x and y, and the joint probability density function is given. X takes two values 0 and 1, and y can take three values 1, 2, and 3. So this is our case. And so here, if probability that x is equal to 0, the probability to have x is equal to 0 is the probability is distributed like this: 1 by 6, 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 equally distributed in our 6 columns. So it is something similar to the uniform distribution, which you may familiar. Uh, so the probability is equally distributed among all these 6 cells. And when x is equal to 0, y can take three different values. When x is equal to 1, y can take three different values. Then the marginal distribution of x is represented by p of x, and that one can be obtained by summing up with respect to y. In this tabular notation, y can take, it's obvious that y can take values 1, 2, and 3, and if you sum up with respect to y, when x is equal to 0, y can take 1, 2, and 3, and the sum is 1 by 6 plus 1 by 6 plus 1 by 6, that is 3 by 6 is equal to 1 by 2. And when x takes value 1, y can take these three different values, and if you sum up with respect to the values of y, then what we have is 3 by 6 is equal to 1 by 2. Then the last column here represents the marginal distribution of x, and that is nothing but the probability that capital X takes the value small x, that is probability that x is equal to 0 is 1 by 2, probability that x is equal to 1 is equal to 1 by 2. That's the meaning of marginal distribution. And in a similar way, we can find out the marginal distribution of y. Y can take three different values. and the probability that y is equal to 1 can be obtained by summing up 1 by 6 plus 1 by 6, that is 2 by 6, that's equal to 1 by 3. And here also we have 1 by 3, and this is also equal to 1 by 3. And when we sum up with respect to the value of x, when x is equal to 0, the value is 1 by 6. When x is equal to 1, the value is 1 by 6. And 1 by 6 plus 1 by 6 is 2 by 6, that is equal to 1 by 3. So this is again the marginal distribution of y, p of y. And p of y gives the probability that capital Y is equal to small y. And it can take three values. Y can take three values, 1, 2, and 3. Probability that y is equal to 1 is 1 by 3. Probability that y is equal to 2 is 1 by 3. And probability of y is equal to 3 is 1 by 3. So that's the meaning of uh, marginal distribution. And this is the case of a discrete random variable. And in the case of a continuous random variable, instead of summing up with respect to x or y, we just integrate with respect to x or y, and we get a function of, say, if you are looking for p of x, then we integrate with respect to y, p of x y dy, and we get a function of x alone, and that's the marginal distribution of x. So that's the concept of marginal distribution. Then to find out the conditional distribution. So if we specify a particular value of x, say it is given that x is equal to 0, then what about the probability that y is equal to 1? If we specify a particular value for x, then what happens to the value of y? So naturally, probability that y equal to 1, probability that y is equal to 1 is 1 by 3 from the marginal distribution. But it is given that x is equal to 0. So that is, we are looking for the probability that y is equal to 1 given x is equal to 0. What happens? So that is given by the marginal distribution. It is p of xy divided by p of x. P of xy is here 1 by 6 divided by the marginal distribution of x. X is equal to, say, x takes values 0. P of x is equal to 0 is given by 1 by 2. So it is 1 by 6 divided by 1 by 2. That is 2 by 6 is equal to 1 by 3. So that's the probability that y is equal to 1 when x is equal to 0. So if you are looking for the probability that y is equal to 1 without any further information about the value of x, then probability that y is equal to 1 is 1 by 3. Sorry, 1 by 6. But if we are provided with an additional information that x is equal to 0, then the probability that y is equal to 1 become equal to 1 by 3. So that is that probability that y is equal to 1 increase a lot when we have an additional information that x is equal to 0. So there we get another probability density function, which is known as the marginal distribution, that is here. And from this expressions, uh, that one can be rewritten in a much useful form as p of xy is equal to, if we cross multiply, p of y given x into p of x. And at the same time, it is equal to p of x given y into p of x. So this is usually referred to as the product rule. Product rule. And if uh, p of y given x is equal to p of y, and p of x given y is equal to p of x, p of s given y is equal to p of y and p of y given x is equal to p of x, then we usually refer to the variables x and y as independent uh, random variables. So if this particular thing happens, then there is one more important property which is to be noted. P of xy is equal to p of x into p of y. So this is the characterization of independent random variables. Two random variables x and y are said to be independent random variables when p of xy is equal to p of x into p of y. Then naturally p of x given y is equal to p of y and p of y given x is equal to p of y given x is equal to p of y and p of x given y is equal to p of x. So this is the characterization of two independent random variables. And as the name indicates, if x and y are two independent random variables, then the occurrence of say x does not affect the probability of y, and the value of y does not affect the probability of x. Those two variables are independent. So for example, if we consider the two random variables, say like the height and weight of a randomly selected person from the population, say from our class, then uh, if I select a person and measure his or her height, that is, our random variables are say height and weight. So we have two random variables h and t, and we have a probability density function pht. Then our question is that whether pht is equal to ph into p of t, whether it is true or not. Then if I select a person randomly and measure his height, his or her height, and it is known, so the a particular height is measured, then if the value of height is given, then does it affect the value of weight? So the second variable is weight, and okay, let us write it as w. Okay, so w is our second variable, and does it affect the probability of w? Obviously, there is a correlation between the value of t and w. We know that there is an obvious relationship between height and weight. Anyway, we cannot write down a simple mathematical expression like h is equal to a function of w. That's not possible. But we know that there is a connection between the value of h and w. So whenever we fix the value of h, the probability to have a particular weight will increase or decrease. So if we have the value of h as 180 centimeter and another value like 150 centimeter, and we are looking for the probability to have a uh, 80 kilogram person, then obviously if you have a 180 centimeter height person, then to have the probability to have a 180 kilogram weight will be much larger than to have an 80 kilogram person when the output is of height 150 centimeter. So that's an obvious relationship. Anyway, the probability will change when the value of h is specified. So in that case, these two variables h and t are not independent, and the probability density functions p of ht and p of h and p of t does not satisfy this particular relation, and therefore they are not independent. If they are independent, then p of h or w is equal to p of h into p of w. So that is how we define independent random variables. And now And now, if we rewrite the product rule, uh, like say p of x given y as say here, if p of 1 minute, p of x given y is equal to p of x y divided by p of x is equal to p of y given x uh, into p of y given x into what is it? It is x given y is equal to um, p of y given x into p of x divided by p of y. So this expression will give the probability that probability of x given y, probability of x given y as probability of y given x into p of x divided by p of y. And obviously we can rewrite it as p of y given x is equal to p of uh, x given y into p of y divided by p of x. This particular rule is known as Bayes' theorem, which is very useful to evaluate the conditional probabilities of x given y or y given x when the marginal distributions are known and the conditional distributions of y given x or x given y is known. So these two results are very useful in our machine learning process. The conditional distributions are very much applicable in uh, machine learning process. So that's about Bayes theorem. And now what we are going to discuss is about some probability density functions, which is very useful. So, so let us have some examples of probability density functions, and let's have some two simple examples for the time being, and more examples will be discussed in our next session. So we start with uh, uniform distribution. Uniform distribution. So there are two types of uniform distributions. One is discrete type, and other one is continuous type. So we start the first one, discrete type uniform distribution. As the name indicates, if you have say an n number of possible outputs or possible outcome for our random process, then uniform distribution distributes the probability of total probability of one among equally among the all possible outputs. A simple example is the experiment of tossing a fair coin or tossing of a fair die. So okay, let's consider the experiment of tossing a die. So if you have a fair die, then the set of all possible outputs are 1, 2, 3, 4, 5, and 6. These are the possible outputs. Then uh, we distribute the probability equally among all these six possible outcomes, and therefore probability that uh, the random variable have a value 1 is equal to 1 by 6. Probability that the random variable have a value 4 is equal to 1 by 6, and probability that x is equal to 5 equal to 1 by 6, and so on. We distribute the probability of 1 among all these six sample points equally among the samples points, and since the probability is equally distributed, it is known as the uniform distribution. And moreover, if we sum up this particular expression, then f of x, the probability density function, is equal to 1 by 6 when x can take values 1, 2, 3, 4, 5, and 6. So that is the probability density function. Or in general, if x is a random variable which takes n different values, that's a general case. General. If you have a random variable x which takes n different points, then the probability of a particular point is equal to 1 by n, and the x can take values 1, 2, 3, 4, 5, 6 up to n. So we define the random variable in such a way that the target space or the output is an integer from 1 to n, and the probability density function f of x is equal to 1 by n. And this is the discrete case, and this is very much useful when we have a situation in which we have a discrete type of output and the probability is equally distributed among all the variables. That's a typical case. If you have to take a lot and make a decision. Say if you have to choose a leader from a class by just taking a lot, then the probability of being selected is equally distributed among all the students, and each student have a probability of 1 by n, where n is the total number of students in a particular class. And therefore, uh, if we do the same thing about a continuous type uh, random variable, or if our sample space is of continuous type, then and if we distribute the probability among all points in say an interval AB, then the probability distribution function is of the form 1 by b minus a, where our random variable takes a value in between a and b. And observe one thing, in the case of a continuous type random variable, we find the probability that say x1 less than or equal to capital X less than or equal to x2 as integral x1 to x2 1 by b minus a dx, and that's equal to x in between x1 and x2 divided by b minus a, which is equal to x2 minus x1 divided by b minus a. This is the probability that the random variable takes a value between x1 and x2. So this is the probability density function uh, of a random variable which has a continuous, which takes a value, a continuous set of values in between a and b, and the probability is uniformly distributed for all values of x in between a and b. Then the probability density function f of x is equal to 1 by b minus a, where a takes a value in between x takes a value in between a and b. Anyway, if we take a value or the function f of x has a value uh, 0 when x is outside the interval AB. So whenever the probability density function f of x says nothing about the probability, then obviously the value is equal to 0. Anyway, for these two probability density functions, uh, we can find out the cumulative density function f of x. We can verify the properties like f of x is always positive, summation for all values of x, f of x is equal to 1. All these properties can be verified, and the cumulative distribution function or distribution function can be calculated for this particular probability density function. These two continuous and discrete type uh, uniform distributed random variables. So these are simple examples to illustrate the concept of probability density function, and these two probability density functions are very useful whenever the probability is somewhat equally distributed among all the possible outcomes. If some of the outputs have more possibility or likeliness to occur than the others, then these two probability density functions are not very much useful. In most of the real life situations, uh, say if you observe the number of accidents occur in a particular city, or the number of casualties reported at a particular hospital, or if we measure the height of a person randomly chosen from a population, all these random observations does not fit a uniform distribution. For example, if you observe the number of casualties reported at a hospital during uh, the one day, then technically the number of casualties can take values 0, 1, 2, 3, 4, 5, 6 up to infinity. But the probability to have one casualty per day, and probability to have 100 casualty per day, and probability to have 10 casualty per day is not exactly the same. Obviously, probability to have 10 casualties and 100 casualties are different. And in a similar way, if you measure the height of a person randomly chosen from a population, then the probability to have a person with 2 meter height and 150-meter height, 150 centimeter height, and say a 100 centimeter height, they do not process or have the same amount of probability. The probability to find a person with an average height is maximum, and the probability to have a person with extreme heights, someone who have very large height and very low height, is comparatively small. So in that case, we cannot distribute probabilities equally among all the possible outcomes. So such a distribution is which is of uniform distribution is applicable only in a restricted number of situations in which we can assume that the probability is equally distributed among the possible outputs. And even though there are a number of situations like the lottery, the gambling situations, uh, tossing of a coin, the coin may or may not be a biased one. But if we don't have any information about the biasness of the coin, then what we can assume is a uniform situation and distribute the total probability of one among the two possible outputs. So that is uniform distribution. And in our next section, we will think about uh, situations in which what we can do in a situation where we cannot assume the uniform distribution as the default distribution. So there we have a lot of other distributions which are known as normal distribution, uh, exponential distribution, Poisson distribution, etc. Many of these are familiar to you. Anyhow, we will come to these concepts in our next section.